Hello everyone, welcome to my channel once again. Today we shall be discussing on how to calculate the exit pressure of a gas passing through a gas turbine. Once again, how to calculate the exit pressure of a gas passing through a gas turbine. A gas turbine has an air entrance at 350 Celsius and 1518 kilopascal with velocity 44 meters per second at inlet and exited at 150 meters per second via turbine duct area of 0.1 meters squared when the mass flow rate through the turbine is 3.26 kilograms per second. Assume heat loss from the turbine is 8 kilojoules per second and the power output is 213 kilowatt. Calculate the exit pressure of air. Take the gas constant of air to be 0.287 kilopascal square per kilogram Kelvin and the specific heat at constant pressure, which is Cp, as 1.018 kilojoule per kilogram Kelvin. Now, let's pull out our parameters from our representation we have. So our given parameters, our T1 equals 350 Celsius plus 273, which gives us 623 Kelvin. Our work out, which is 213 kilowatts, which gives us 213,000 watts. Our Q out, which equals 8 kilojoules per second, will give us 8,000 watts. Our inlet velocity of the gas at the inlet of the turbine, 44 meters per second. Our exit velocity of the gas, 150 meters per second. The area of the turbine duct given, which is 0.10 meters squared given. Our inlet pressure at the inlet of the turbine, which is 1518 kilopascal given. And don't let us forget the mass flow rate, which equals 3.26 kilograms per second given. Now, how do we find the exit pressure of the air passing through the gas turbine given here? Now, by using the steady flow equation, which is this conservation of energy, our Q1 minus Q0, which is the heat entering minus the heat going out, plus the work entering minus the work going out, equals the M and the gradient of the entropy plus the variation of the kinetic energy and the potential energy, which is given. Now we know that the heat energy entering is nullified, the work entering is nullified. Also, our potential energy is nullified, so there's no variation of potential energy. Now we have the variation of the entropy plus the kinetic energy being given. Now from here, we have our Q0, which is out, plus work W, which is out, equals M H2 minus H1 plus V2 squared minus V1 squared. Now from here, don't let us forget our QO plus WO equals MCP T2 minus T1, because the variation of entropy equals MCP T2 minus T1. So that equals H2 minus H1 equals MCP minus T2 minus T1 plus the variation of the kinetic energy, which is V2 squared minus V1 squared over 2 in bracket. From there, we can pull out our temperature first, the exited temperature, which is T2, which gives us T1 plus V1 minus V2 over 2Cp minus WO plus QO over Cp multiplied by M, which is the mass flow rate. From there, we have our T2, which equals 623 plus into bracket 44 squared minus 150 squared over 2 multiplied by 1.0018 times 1000 minus 21300 plus 8000 over 1.0018 times 1000 times 3.26, which is being given here. Now we have our T2 being calculated, which is 546.31 Kelvin. Now, by finding the second temperature, now to find our exited pressure, we have P2 equals V multiplied by R T2. Don't let us forget our mass flow rate, which is M over A2 over V2 times RT squared T2. Now, don't let us forget our R is a gas constant, which is being given 0.28. Our calculated temperatures 546.31 multiplied by our V, which is the volumetric flow rate times the temperature. Now we have our P2 equals our mass flow rate, which is 3.26 over 0.10 multiplied by our V2, which is 150 times 0.28 times 546.31. Therefore, our calculated pressure to exiting the turbine equals 34.08 kilopascal being calculated. Thank you very much.